because now we're getting to actually the things that are not just straightforward. Verticality monitoring and allowing for it starts to get complex and it's not easy to easily draw diagrams to show it, right? So you've got to get some things in your head to start with. If you've got on the left-hand side here, if you've got a floor above another floor, treat it like we did in the deformation, right? That point you put up could be truly vertical to the center of the next floor, but that floor could be twisted, right? Tilted in two directions, right? That's the sort of option. Let's presume the floor is pretty flat. They're your options. We tilt like that, tilt like forward, right? Or twisting around. So there's 3 degrees of freedom, we would call it. And the difference between that center and the center on the top would be the small delta x, delta y, right? If you actually know what that is, you actually can define some of these parameters. So if we had that, and you put a plane through that point, and we're talking about very precise measurements here, right? And you see that you've actually got an x, y, z, right? For 2 points. Once you've got 2 points on an x, y, z, you can actually define a line, and that line will have a plane that can rotate about it, like this is here. So that's why we've been pushing with metrology and deformation to think a lot more in terms of planes than you do in terms of just lines, right? Because the intersections of planes that define the point. So the magnitude of it being out is really a 3-dimensional magnitude. And you come back to this, but we'll come back to it later on. You probably think at this first stage you're putting out one floor. Surely it should be easier than that, right? But as it gets more complex, it gets a bit more difficult. So that defines a tilt, virtually, a tilt in the floor. So there's 2 ways of looking at it. And Zara's put that photograph in because she was just in Italy not that long ago, and I think she took the photo. So it was her chance to get a nice photo. It's a very nice photo, actually. But direct measurement of the verticality, right? Or indirect measurement. Now, you're mostly used to direct measurement. Most surveyors are, right? You either set out directly or you measure directly. In most cases. So the direct measurement, optical or laser plummets, they work on the same principle. Okay, there's no change there. You know, people seem to think that this laser is different. It's still the same prisms that goes through. It's just a laser beam. Right? Defining the vertical with a total station. Okay, that's, in other words, we'll come back to it. You just tilt the telescope vertically and say that's it. Right? The next one, total station offset measurement using ATR. You've probably never heard of this until I read how they did Burj Khalifa. I'd never heard of it, and I think it's one of the most incredible examples of an Australian surveyor who actually solved this one, right? Coming up with something that's just out of centre field, like to start with, and then going, if I think about this a different way, I can use an existing equipment to get a result. Very, very clever. And the last thing is offset to a vertical line from, say, a total station or even a theodolite or some tool that's optical or laser. So laser plummets, you won't go through the old-fashioned ones because they're never used anymore, right? Generally speaking, are some sort of suspended pentaprism, exactly like an automatic level. So the line of sight, if this is tilted, right, the line of sight isn't tilted. You know, the principle of an automatic level, everyone should be fully aware of that, right? So this is actually a standard optical plummet. Now, there might be a lot of things attached to it. It might read electronically, right? It might use 2 beams, right? There's lots of differences, but the principle's still the same. You can get like a construction unit, and this is, by the time you write this stuff, it's usually out of date, right? But 20 metres, yeah, I think that's actually about right. If you went down to, not Bunnings, but if you went to, I don't know what in Brisbane, one of those tool companies that, you know, sells builders stuff, right? Yeah. If you bought an optical plummet, which is normally often part of a rotating laser level, right? They combine. This 5 millimetres over 20 metres is about right, okay? For building construction, it's not a problem because most builders are worried about them coming from this. The floor's 4.5 metres high or 4 metres high, right? You know, and I want to go up there and I want to be straight, I'm 1 metre away from the, you know, my RSJ here. So when I get up there, just go 1 metre over and that's where I'm going to put it there. You know, not terribly complex. For the surveyor, of course, that we're presuming the builder makes mistakes and everything else, so you've got to be that 3 to 5 times better. But there are units, and I think the study book outlines one of them, I can't remember the name of it, that's running around the 1 millimetre per 100 metres, which is pretty good, right? Of course, you pretty much get what you pay for, right? And also in terms of time, in terms of setup, their ability to resist, there's some things now that they resist vibration a lot better. So ones that are designed for construction, you'll find have a slightly different pentaprism system, right, a compensating system. Okay, the range is important for high rise. Okay, if you can, you don't want to just going, I'm just going 1 floor at a time, because you know the propagation of error is just, you'd like to go, can I measure 5 floors, then come back and interpolate, right? It's going to be more precise. Don't forget, it's still a laser beam, so it's still affected by the environment around it. So by dust, haze, temperature, pressure, right, and even humidity. Lesser extent, but it is affected. Most of the better systems are like 100 metres to 200 metres. And the beam footprint, which is the divergence of the beam, you don't often see this in surveying because most of you work in the daylight, so you don't actually see the laser beam, right? When we stuck one up in this room, a cheap laser, it would probably be about 50 mil on that wall, right? About that sort of circle. I actually don't know what current total stations would be, but I'm presuming less, a lot less, right? There's a figure in 2301, I think, we did for the divergence of the beam. But it's important for this because if you're measuring vertically and someone's actually measuring it on the top, right, you know, too wide a divergence, there's too much range of error. Now, when they use these systems, right, they do have special targets. So in both metrology and deformation, we mentioned some of the targeting, right? The better targets, and even the cheap rotating laser levelers, right, have targets that intensify the appearance of the beam. They can't intensify the laser beam, but they react better to a laser beam, so it makes it more visible. So these guys are laying out ditches in daylight, you know, and you've got a rotating laser level. You mostly don't see the beam, right, but they'll see a reflection of it there, you know, because they're using better targets. Absolutely critical here. And you'll see quite often the targets are such a point they're actually bolted into the floor, and they've got scales on them. So when you measure up, you can actually see the scale. You can see the beam point, right? You know how far it's off. And then you put a mark on there for where the center, in other words, the most precise point from that point there to the point vertically above you. Right? Most cases, we don't mention it, but in super high rise, there has to be some account of the deflection of the vertical, right? Because buildings operate on gravity, right? If you're using this sort of equipment, you're using gravity, it's fine. If you're using something else, you may be presuming that the vertical is a right angle to the ellipse, the ellipsoid, right? Which might not be the case. It's not usually as big an issue, right? The special targets are something that makes life a lot easier, but very similar to targets you would use for total stations. Okay. Vertical plummets are usually in a stepped approach, so it depends on what step the range of the vertical plummet. And you'd have to look at plotting range versus precision. You know, sometimes it's not linear, right? It can be curvilinear. So you go, if I do 3 floors or whatever, I stay within the precision. If I go past that, I start losing it. You can see there the standard deviation, that's a 95% on a good piece of equipment, right? So over 200 metres, you're getting plus or minus 5 millimetres. It's pretty accurate, right? That's through a step-up process. Now, that's actually the ideal situation, and most laser plummets, optical plummets, are not quoted as like, you know, plus or minus this. They're usually quoted as plus or minus so many seconds of arc. So then you've got to calculate what that converts to in terms of off the vertical, right? But don't forget, when it says it's plus or minus, it doesn't say it's plus or minus in one direction. So you're talking about it subscribing a circle down here when you're stepping up, right? You're starting to propagate error. So once again, the random error probably isn't the biggest issue. Systematic error is, right? Now, if you see on the right-hand side here, this is in a German building that was done without the fancy technique, but this was pipes through the floor. So their plumbing was done up through piping, I think over, if I remember correctly, over 3 floors at a time. And then piping was dismantled once they transferred it. Now, then you've got to go back before and go, if you're using that method, right, to control, because you've got no other method, then you've got to have redundancy. Now, outside when you're doing surveying on a floor or even the first few floors, right, you can put redundant. But when you're getting up here, we're talking about redundancy means putting another hole in the floor, another pipe. Because 2 points, think back to that plane, if you've got the 2 points, it defines a line, right? It doesn't define exactly where the plane, yeah, in theory, that floor could be floating like this, right? So you could put the 2 points up there and you could level then and go, it's not doing that. You know, I can see it's flat, right? Which helps. Usually you would aim to have at least one more redundant point. Now, the redundant point might be a redundant point of the same methodology, right? Or it could be, and which is preferred, a redundant point using a different methodology, because that then is a blunder check. So we're talking about maybe GNSS, resection using a total station, if it's possible, right? Things of that nature. But this is a fairly accurate method. You can see here, it's very hard for you to see, but maybe you can just see it on the, what he's looking at there is a plate sitting on top of the floor. The plate's gridded, right, it's transparent, and right in the middle, it is a bit difficult to see, is a red glow. That's the laser beam. So he positions this plate to where the laser beam is, right? And then most likely, depending on the circumstance, someone will set up on that and set out other points on that floor, right? But you can see you're going to need at least 2 points, and really to cover anything else you need a redundant 3rd point. That defines the plane of the floor and gives you some redundancy. So the piping on the right is like steam piping, like 200 mil steam piping, that type of thing. There are some issues, I think I mentioned in the study book, that, of course, the environment inside the pipe could be different to the environment outside. But generally speaking, is a preferred method because you can control the environment of the pipe a little bit better. There's not wind blowing across it and things like that, right? It probably has a better temperature regime. Okay, defining the vertical with a total station. Literally, you get a diagonal eyepiece, which are available. Not many people use them. People in mines are used to using them. That just means that you probably notice if you swing the telescope, it's really hard to get your head underneath because the rest of the instrument's there, right? So you do use a diagonal eyepiece to actually see it. Now, I haven't got a diagram here to show you, but you should be able to see, obviously, that that's fine. Everything that we talk about normally face left and face right now converts into the vertical. So if there's an error and you swing the instrument around, you're going to subscribe a circle. Can you see that? So just imagine this is the true vertical, right? When you put your telescope up, there's a small error, so it's like that. Now, if your rotation, if the instrument's level, that's a big if, right? Because it's got to be really level, right? Better than your normal setup. I mean, you can actually calculate this. You know the automatic compensator on a total station? It normally says, you know, you can set it up to plus or minus this. Most surveyors go, well, that's not going to affect the horizontal angles. It won't affect the small vertical angles very much at all. So that's fine. That's good enough, right? You know, but if you're trying for true verticality, it can be an issue. The main thing is that if you did rotate that instrument and it was reasonably level, then it should, if it's an error, it should subscribe a circle on the top. So it can be done, right? You'll probably find in the field it's a very fiddly thing to do because you, to subscribe the circle, you've got to be able to move it around. So you've got to access right around the instrument, okay? You're looking at it, so it's visual, you know? And usually you're going to try to read how far you think it's off by reading the zenith angle, which will be somewhere like, you know, 0 degrees in a second or something, right? So it's not bad. So, okay. So you observe on 2 faces, you do the normal surveying things, right? And then you rotate it, usually through 3 positions so that you can actually plot it, you know, where it's out. You can get high precision, but it's a more fiddly thing. if you want to make an estimation, about 2.5 seconds over 100, 150 metres. Now, you know automatically from the formula that's always in your head, right? Aside from the one that wears their cheap petrol, right? Is that it's half as many seconds in millimetres per 100 metres. Right? So if we're saying it's 2.5 seconds, we're saying it's like 1.25 millimetres per 100 metres, give or take, right? Okay. To be effective, you should use the same aperture system. That's the pipe in this case. You won't see that very often. That was done in a very sophisticated construction. You might see holes in the floor, right? But there's no issue using one system over here and one over there if they're in totally different environments, right? One way around that, because it's not too complex to do, is actually do it at different times of the day, swap the instruments over, something of that nature. Just get as much random redundancy as you can, and you're more likely to be correct. Okay, this is a... I'll just start off with the general thing that it tends to be better than using a total station in the vertical mode, right? You can also measure the distance, which you could do with a total station, which is handy. And it has actually, there are applications. Now in this particular case, this is was developed on the Burj Khalifa. And because Leica was the instrument manufacturer who developed this and the other system I'm going to show you in a second, or sponsors development, I should say, they actually have a thing called Zenith Line onboard application. Now, I haven't got papers here, but I've seen some other papers that other manufacturers have got their own version of this now. But this was virtually unknown before this, right? So it's a good, so it actually is lower. It's an acronym, you know. So if you see an engineer and they say, how are you doing this? You say, I'm using this lower method. You'd say to you, you should use the faster method. If the building's dynamic, so that's like 10, 15 minutes, that's a pretty poor joke. Right. If the building's dynamic, so we've got that 10, 15-minute movement, right? The number of total stations would be needed because you've got movement. We'll come back to that a little bit later as well. And the laser, the sight, line of sight, everything else is still subject to refraction. There is still some refraction vertically. It is less, but so refraction's less of a problem with these sorts of methods than they are with others. Now, to do this properly, you should actually go back to your SVY 2301. There's a description there of ATR, automatic target recognition, right? And how it works. I didn't repeat it because I presume you'd love to go back and reread that stuff. But basically, there's a falsehood some people, even surveyors, think that the automatic target recognition is the instrument moves onto the target precisely. Okay? You've got to remember the line of sight is a little bit like your eye. You know what it's like when you're lining up a target and you can look at it and think, that's right. You look away, look back again, it's moved, right? You know what I mean? There's movement all the time, right? Now, if you did that automatically or robotically, then what would happen is it just would be there all the time, trying to actually define it. So what actually happens, and this is just a review aspect, is that you have an image of the target taken by the total station, right? And it compares the image of the target to where the crosshairs are. It's all mathematical. And says there's a delta X and a delta Y. That converts to minus 1.3 seconds in, vertical and plus 2 seconds in horizontal. And it applies that correction to your angles and distances, right? Both vertical, horizontal, angles and distances. So you go to another target, it might be totally different because the image might be different. So it changes all the time. Now, where this was clever was that the person, this is well known, right? But when they were looking at this, they're saying, when you've got to like 800 meters up, you've got a lot of floors. So you've got to start thinking, you're going to repeat this type of measurement many, many, many times, right? So A, you want it to be as accurate as possible or precise as possible. B, because you're going to repeating it, it should be efficient, right? So that it's worth the effort to actually think about it first before you go along and start buying a diagonal eyepiece and just going slowly around everything, right? So what they found, and this was with the Zeiss equipment at the time, and Leica equipment, was that that's what it does here. If you look at the center one, right? Forget it's a zenith line. Just imagine this is in the horizontal. It measures that compared to the machine axis. right? Delta X, delta Y. What the guy who did this, who was, I think, actually the guy who started was a Belgian chap. He suddenly found out that when he looked at the specifications, that in that particular case, Leica stored that data. Even though it's like, if you point to a target, they only needed it for that round of angles, right? There's part of their data file stuck at the back somewhere. They actually stored it. So what he worked out and said, well, wouldn't that be clever if you could just put a prism upside down, right? Use the instrument looking vertically, using ATR, and then actually having it download and say it's actually 1.5 millimeters, or the equivalent of, right? You can calculate it, to the north and 2.3 to the west. Pretty quick. It's digital. You keep the data in case there's a problem later on, right? And because it's quick, because it's a laser beam, you can start to do, if you're not measuring like that, you're only using a prism, you're starting to say that actually the hole through the floor can be a lot less. Right? It's got a lot of advantages. It's not the be-all and end-all, but this is actually an example of an example you should take account of. Too often surveyors think you learnt these processes, right? You should be starting to think, I learnt how to think. I learnt how to think in 3D. I've learned how to actually understand what the technology actually does, right? Because this is only one example. I'm sure there are lots of other things that if you looked at and you went, how do I do that, right? So the gyro theodolite, or gyrototostation, it's called these days, right? Is well known. It was developed in the 50s, I think, right? It was developed by Gordon Louth, a South African professor, right? Who actually did that. He actually taught me. I mean, he was very old when he taught me. I was very young, he was very old, but apparently that's the way it happened. He told the group this one time, literally, he thought, well, what you really need underground is like a gyro, like they have on a ship. Because you can't see anything else. And anyone who's worked in a mine knows how complex it is to hang two wires and try to get a bearing off it. It's really hard work, and you don't feel confident when you've done it, right? So that's firstly what he did. He thought, well, what would happen if I got a gyro and I sort of stuck a theodolite into it? Very complex in mathematics, but he was a brilliant mathematician, right? Won the highest civilian award in the Second World War for cracking the German map codes. The Germans used their own map projection system and their own Earth-based system, and they made it up so that the others couldn't work out the coordinates. And he used what's now called Louth's transformation to be able to derive the parameters, and which made a fundamental difference, particularly later in the war with the bombing raids. Right? So this is an example, really simple to do. I could see some of you would actually get in a situation if you think, okay, that's vertically. Why can't I do that horizontally? In other words, if I can download that data, if I'm doing precision work, say in a tunnel, why not record how far it's out from that particular prism mark, right? Because you can do it in reverse as well. What happens if you put a prism bolted to a wall? So it's there, same prism all the time. You start reading to it. Where you're reading, if you get different offsets, that gives you an indication of where you are. So never be scared of going a bit out of left field, right? So this was the preferred method on the Burj Khalifa. It wasn't used on the large German project, right? So there are things, people prefer different things, right? This is, of course, getting up to so high compared to the German project that there was a difference. So there's a European bank building on the German project. So the diagrams there are straight out of the study book. They sort of explain it, but if you get that concept right, it's pretty easy, right? And the last one, which isn't impossible, is you take say from your control, right? You define a plane, by line of sight, laser, and you actually measure out, right? Now this seems a bit odd, right? But you'd be surprised how often this is used because, number one, it's really easy to stick a prism on a stick, rather than have something outside the building, right? So you can actually go from the side of the building and hold the prism out, right? And where it intersects, you can say, oh, that's 1.8, 2.3 meters out. And then you start to get a cloud of points to go, where's the fascia of the building? You could use it with the columns even. You know, very good application for maybe a blunder check, right? And also for deformation checking because fairly easy to do, relatively easy. And a little bit like leveling, if you remember back from when you first learned leveling in surveying A, right? Which I'm sure you learned it very, very well, is that when you hold it out from the building, how do you know that you're right next to the building? What you do is you move it, right? And the shortest distance will be the answer. You know, exactly like a staff. You know, doesn't matter where you sway it, the lowest reading will be correct. So not as much for super high rise because you're looking too far up, but for low rise, it's a very valid technique, particularly where you would have seen in construction surveying often you set out 4 corners offset to the building, so you actually have that line that you can look through, right, quite easily. Okay, the geotechnical ones, this is actually, if you look on the right-hand side here, these points here, that's a tilt meter, it's a bit hard to read. They're all tilt meters, right? And that's a tilt meter. There's one right on the top. So we're only talking about the indirect methods. So you're not actually measuring. The tilt meter passively measures what the tilt is. Now, don't forget inclinometers, they're often called as well, right? You've got to be careful. When they say they've got a tilt meter that measures in 2 planes or 3 planes, right? If we put a tilt meter on this floor and it says it's tilted, right? How do you know what direction it's tilted in? Yeah, it might say, okay, it's tilted this way because we put the box on the floor, right? But how do we know that's not tilted more this way and we're just on part of it? It'd be like strike and dip in a plane, right? So tilt meters can be smart. The expensive ones are smart, right? And they have lots of ways they work things out. But the end result is usually a tilt. That's what it is. You get a number, right? So that's why locating them critically, they've got to be in critical points. You want the tilt meter to give you data. So in this particular case, these points would have been worked out with structural engineers, probably in consultation with surveyors, right? So where, as the building got constructed, where there's actually measurement of these tilts continuously. Then there'll be, right back to the very beginning, the structural health, which has to go on forever, right? Those same tilt meters will be used for that. So you're starting to see with this high rise, it's not a matter of just the surveyor on site, right? Setting out things. This has a data center that's collecting all this data. So tilt meters are one, right at the very top there. The reason it's at the top because you can't see satellites from the middle, right? Is GNSS is ideal for continuous monitoring because it's a passive system. You know, unless someone shoots this satellite out of the sky, it goes day and night, right? And it's a very consistent system. Okay, so once you set it up, it's a great monitoring system. And you'll find on most high-rise that's might not be used during the construction, but the end result is they'll usually, as part of the building health, right, there'll be a GPS or two, right, set up, or a GNSS receiver at some point. Constructors sometimes avoid because they're not cheap until they have to do it. Okay, so that's a tilt meter. This is a modern style one, right? Has data inputs. Really, it's just a box, right? And you can see the output here is actually movement, a bit like a seismograph, right? So the change in tilt is measured. They're not super cheap, the things used in buildings, but they're cheaper than surveying. Right? So you put them in, you probably leave them. Most of them are now connected. Not that long ago, they'd be connected by what they call RJ45 cabling, right? Which is a bit like Cat5, Cat6 cables, right? Nowadays, they tend to go to somewhere fairly close and it's wireless. So instead of trying to wire the thing up, they'll put it somewhere close and then have some sort of wireless router, right? So that's a fairly typical one. Usually key floors. I mean, 50-meter intervals is the sort of stuff I've read in papers, right? So it's a fair way apart, right? Where static movement is predominant. So we expect static movement. Dynamic movements are expected. Tilt meters become absolutely critical, but their location becomes critical. So the dynamic movement is, say, skewing, right? That may not affect the tilt meter that's lying flat. It would only affect the tilt meter that actually measures that angle. So if you really wanted the perfect world with simple tilt meters, you put 3 in. You know, you put like one that way, one this way, and one up. Right? There are combined 3 axial tilt meters, so you can get them. they're dearer, right? They do operate in real time, obviously, right? And this co-location is the sort of big buzzword with all the construction these days, is co-locating instrumentation, right? So you link the GNSS antenna to the tilt meters, to the inclinometers, to the piezometers, right? Whatever other method you're using, right down to your total stations, right? So it's a holistic approach. So as a junior surveyor, you might actually be doing some of this stuff, right? As a senior surveyor, you might be asked to set up a data collection center, integrating that data. Now, where that's important is you're talking about, in a lot of cases, real-time least squares adjustments on the fly, right? A mix of data sets. Now, you're probably trying to get software to do that, but it's very important you understand what's going on behind the software so that you understand what you're likely to get out of it, right? Okay, GNSS is reasonably obvious. Everyone should know by now how it works. In our building environment, one of our biggest problems is just the nature of it gets better as the building gets higher because you start to get to the skyline. It's usually terrible on the ground floor because you build in the middle of an urban centre and your sky angles can be a few degrees, right? Which, even though we've got a lot of satellites up there, that's not anywhere near the optimal, right? So, pointing out again, you're most likely only using, for high-rise, always different methodology, different instruments as the building goes up. You have to be prepared for that. Okay. This is the example of the last sort of thing we'll do of the Burj Khalifa, not because it's the highest building in the world, because it required a rethink. When they were going to build this, they had to rethink the engineering, had to rethink the materials, right? And they suddenly realised there was no surveying method that could do this. You know, it was a problem. The engineers said we need this sort of control on the construction, you know, at 750 metres up at that point, right? And surveyors were going, well, it can't be done. Literally impossible at the precisions they wanted. So this is one of the first times in many, many years where actually the surveying profession has been challenged to something that was pretty much new, right? Now, this doesn't work for every single system, and it certainly isn't cheap, right? But we're just going to go and try to explain how it works, because you'll see some papers on it. They're either very generic and they show lovely pictures of the things set up, right? Or they're incredibly mathematical and you sort of lose sight of it. So we're going to try to get somewhere in the middle. So if we look at this on the left here, this point here, right? And we're talking a building that's straight, right? And we're going to use terminology that you've probably never heard, dynamic surveying. You've probably never done it. Actually, you probably never will do it. But it is dynamic. So most of the time, you actually set up either the target or the measurer, right? And you're static. You don't move, right? You stay there and measure. You might measure over time, so you may have the time aspect, right? So you measure every minute, you know? But you are actually set up in one place. Dynamic surveying says that you're actually holding the tripod, right, with a total station on top, and you're going like this, you're moving. And you're going to be reading everything at the same time. That puts it into a new focus. Number one, it makes it really hard to level the instrument while you're moving, right? So you see how it goes completely out of our thinking, the way we think about things. It's a leap, not quite as big as going from traditional surveying to GNSS, but it's a leap all the same. But surveyors for generations, I mean, we have now EDM and, you know, precise measurement and things like that. But we are still standing in a place measuring angles and distances. We're still doing the same stuff, right? We don't actually, you don't see surveyors, hydrographic surveyors, go on a boat and set up a total station and go, okay, I'm going to measure all the targets, you know, and the waves are going like this. It doesn't happen. So this was their problem, because once the building got to a certain point, and I think, I don't know if I mentioned that before, but there's a sort of critical point at which your traditional surveying goes out the window. And it's about, for high-rise, 150 to 200 metres. You start getting, not for every single case, but you start to get to the point where you can't have control, because you're not going to be able to see everything, right? Your vertical plumbing starts to lose out, right? The precision starts to fall apart. You have to come up with something different. Okay, So with this particular case here, if you look at the center one, if this building's moving, I haven't got this in 3D, so you can imagine that, try to imagine in 3D, then there's going to be tilts, right? At least one. So the building tilts, could be that way and that way, right? But there'll be a vector that defines that tilt. Right? So if you can ascertain that, now in kilometers, you put one on this side and one on that side, it says it's inclined at 1.31 degrees and the other one's inclined at 1.77, you can calculate the vector using cosine directional vectors, which you'll remember completely from the metrology module. So looking at reality, is what we're saying is there's the center column. We'll just use the center column for simplicity, right? And also because in the Burj Khalifa there was a center column system, a core column. Then you're set up in the total station here, right? Your vertical in the total station, when you level it, is really vertical. Not right angles to the floor. Can you get that picture? Right? So we have X and Z here, and then Y coming towards us. This is the true vertical line, right? This is the center line. We've got to assume this floor was okay at the time. But, you know, the wind's blowing and the temperature's gone. The whole thing is moving, right, in real time. So this is the center of the top of the column if it was vertical. If the formwork guys come out here and actually set that out, right, then they're going to go, if we go, well, actually, we'll make it vertical, they're going to put the column up there. It's not right angles to the floor. And this floor is in 3D. So when I say not right angles, not orthogonal, right, it's not orthogonal this way nor that way. It's some point in space. So what you want is that you want to put up the formwork. So when you pour that concrete and the building returns to state zero, right, that it actually is vertical. Now, it may never, this is where it's hard to conceive, it may never actually return to state zero. It's possible. You know, the wind might always blow, the sun might always shine, right? The state zero is the design for the structure. So that's what you've got to build it to. So if there was, say, a wind of 30 kilometres an hour that blows all year, right, the structural engineers will have designed the building at a state zero that resists that. So you've still got state zero. So your trick is, how do you get the formwork, well, this is formwork at this moment, just imagine circular column formwork, right, for simplicity. How do you actually get this formwork up here so that when the building straightens up, it actually is truly vertical? You see the total station, it looks a bit skew with, right? So it's not horizontal for a start, right? But its vertical plane is vertical. If you sort of keep this in your head a little bit. Okay, the reason you do that is that the ground control's too far away. I think I'll show you a diagram there somewhere. If you look at the Burj Khalifa at 800 metres up, I think we calculated the reasonable angle, you know, using air analysis, right? You'd have to be like 2 kilometres away for it to actually be useful. Well, 2 kilometres, desert conditions, you know, you just lost all accuracy. Okay, the vertical, carrying up your verticality is getting to a point where you can't do it anymore. And also, if we go back to that diagram, if we set up a laser plummet, right, you know, even though it's all laser and digital, right, it's going to be vertical like that, even though the floor is like this. You know, because it finds true vertical. You got to remember, on the Earth, we're lucky with that, is that gravity is something outside our control, whereas angles are just all relative. You know, that's nothing fancy. There's no such thing as a true angle. It's just a measure between one point and another. Because as the height increases, and this is the thing that actually became the really critical issue for a lot of buildings, was that as you get to that height, people were saying, oh, we could use that same method we used, you know, for the 30-story building, right? And they're going, well, yeah, that'll work fine. But what the design engineers found out is that, of course, as you increase in height, your dynamic forces are also increasing. So the wind is not now 20 knots. The wind is now 70 knots. You know, the effect of ground vibration is magnified. The harmonic motion of the building is magnified, right? So what you thought you could get away with down here, you won't be able to get away with at the top. And you do have to do it. I mean, if you look at that diagram, it's the current method of construction. If you look at the old construction methods, like the Empire State Building, you saw they tended to build a frame, a bit like Meccano, put all the things in, put the bolts in. That's that. You ever see the old method? They had these massive, great spanners, right? Looks like a bit of fun, but then you could sort of say, well, you can go up because you're resisting the wind movement as you go up, right? Because you're just got a framework. You still have to do things, but now the current construction methods are to, you build depending on your construction thing, but the crane might be here, 4 floors below, they're actually putting the walls in, you know what I mean? And as the crane moves up, and then 1 floor below, they're pouring or letting it settle. Where the crane is, they're pouring, right? So that's where the formwork is. So that's sort of thing of how do you set out the guidelines when the building's moving. Okay, and also as you get to a higher level, if you think about it from a physics point of view, that crane used at the lower level, right? The one you got in the higher level is actually probably a bigger crane. Might be the same size, but possibly bigger because you've got, number one, it's going to have a lot more wire because it's really a long way up. Right? And often you need different size cranes because they won't just use a 90-ton crane to pick up a basket of rubbish. It's inefficient. So what happens is the effect of the crane load, right, at the top is greater, just for the sheer distance. It's just a bending moment. Okay, so when you think about a normal surveying problem, you want some sort of orientation. Now, we're not talking about north-south here. We're talking about orientation to do with the design, right, which is related to your control on the base. You need to be able to resolve those dynamic forces. So the wind pressure needs to be able to resolve in terms of a coordinate system, X, Y, Z, impact. So you're really talking about a vector in space. You obviously have to have redundancy because there are so many things going on at once that the only way you're going to get solutions by having enough redundancy and ensure there's no systematic errors. And you have to resolve every parameter and all the movement in real time. This is the other different thing. It's not like, the Leaning Tower of Pisa is bent, right? Well, it doesn't move, 3 inches every day, right? But we're talking about here, that building is moving once every second. We're pretty much close to it. So there's no use you sitting down saying, I've worked out the parameters for the building. Oops, changed. I worked out the parameters for the building. He'll be there all day. So we are talking about pretty close to absolute real time. That's a very, very complex equation to put into play. Okay, and the positioning of the construction reference points, there's going to be a lag time. So you've got someone there, you say, yeah, that's where you're going to put the center of the column, formwork, right? And the guy says, okay, I'll do that. And you say, no, hang on, we're moving it because the building's moved, right? But if you actually go through it mathematically, if you do it correctly, it doesn't matter if the building moves. But you should minimize the lag time between the two because there are other things that come in time between the survey and the construction, which means the surveying is going to happen while the construction is happening. That's what it really gets down to, which is not easy. Okay, the solution. Now, can I just go ahead here for a second? Yeah, that's right, make sure it's there. It's really called the hybrid system. It's actually got a core wall control system. You can actually go on the internet if you want to and look up the Leica core wall control system and you'll see the US patent for it. That explains sort of how it works, right? So they've actually patented the process. They did this partially because the guy who developed it mathematically was actually a Leica agent in Belgium. So in this particular case, try to get the scene here. I just want you to make sure you understand. So looking on the right-hand side there, that is the Burj Khalifa, right? So it's 830 odd meters high, 160 floors, 3 basement levels, 460,000 square meters. I mean, that's a lot of property, So what's a house in Australian capital city? How big? Well, you bought a lot of houses. Well, 1,000 square meter property is pretty big, right? So most parcels in a place like Brisbane now are 504 to 600 square meters or something like that, right? Yeah. Okay, so just get some concept of the way this building is construction. Every 7th floor, there was a cutback, so it gets smaller, right? I mean, you pretty much can't build a building bigger at the top than it is at the bottom. That's pretty hard to do. Okay, I'm just going to explain this because it actually is a concept that's a bit difficult to get through. This is the set out for it. I'll come back to it on the next slide. They have 3 or 4 GPS receivers, right? On the right-hand side, you'll see a base station. Now, that's one base station. It could be more than that. Obviously, fixed, well-known position, located in a good spot. I mean, just presume that. So you have at least the 3 of these. I mean, you could have more, but of course there's a cost factor here. In actual fact, the mathematical solution is possible with 2, but there's no redundancy, not enough redundancy. And you have a total station on the floor and you have a bunch of prisms, right? And presumably people to hold them. So if the target floor has no tilt, then it's not a big issue, right? You can sort of see that you could use those GNS receivers to orient the floor and the total station to set out things. Pretty good, right? So you're just replacing what you would have intersected before from the control with better quality GNSS, right? Now we're talking about very fixed here, so if you actually look at the images of the Burj Khalifa, you'll see that they've actually got bolt arrangements. It's part of the construction for the receivers to go onto, right? And the receivers are, you'll see them better in the study book. They look as though they're specially made. They're actually just been adapted. So there's a 360-degree prism between the receiver and the tri-bracket. Just makes it one unit. I think just to make it simpler. Okay, if the floor is tilted, there's an immediate problem that you're used to using your dual-axis compensator. Now you'll know in most of those, if you look through your total station manual, it will give a certain point at which it doesn't work, right? Okay, which is actually, in most of them, it's about the pill bubble. If you've got a pill bubble, it's about going outside the pill bubble, roughly that, right? I think 5 seconds or something like that, right? So, but the tilts here we're talking about go past that. So number one, you can't level the instrument properly. Well, you've got to presume you can't, right? The compensator also gets affected by vibrations, like we're talking about with levels. So there's also that issue as well. To resolve that part of it, right, it's really simple. You turn the compensator off. Don't get tempted to think it's actually working. Because it's not working, if it comes in and out of working, you don't want it making corrections, right, when it's unsure. It might make a correction for 1 second, then a second later, it's can't do it, right? So you tend to turn it off, right? You do level the instrument. You do it manually, so there's no electronic compensation, but the instrument's still going to go off level. You're only doing it manually so it's just somewhere near it. Okay. So with the total station, you're going to observe to all the prisms, right? And we're already talking about frameworks here. So the prisms, which are part of the GNSS receivers, they will have continual positions, right? Logged, whatever the logging rate is, but you can determine the logging rate. Let's presume it's near real time, right? You're going to measure usually robotically, right, to all these points, and these are going to be our control points. They're the final measurement, right? But you tend to do it all at once. So it's all happening at the same time. So you've got angles, distances, right? Vertical, horizontal, the whole bit. And you've got GNSS, NMEA data, right? Rhinex data, just pumping out all the time. If you add another GNSS antenna, you get more redundancy. In actual fact, even though it says here, provides redundancy, even with 3, you are getting some redundancy, right? But it is a cost factor there because, we're talking about dual frequency, top-level receivers. They don't come cheaply, right? Most surveying firms are not going to say, I just happen to buy 4 of them just in case I need it, right? That's not going to happen. Most surveying firms that have one they could use as a base station, probably a lower level one they're using as a rover. That's, I suppose, normal. Okay, the second core station also provides redundancy. Now that never used to be an issue, but see, now we're getting so many core stations that you setting up a base station and using a core station as well as an auxiliary baseline, right? You're improving the precision. Okay, so that's all the equipment, but of course, it's still a fair bit of equipment, right? I mean, you're talking about a high-end total station, so you've got over $50,000 there, right? 3 receivers. I don't know, what are they worth these days? Anyone know? Don't think you get much change out of the $15,000 to $20,000 range, right? So special setups with the prisms. I mean, all has to be adapted, right? So it's a special made system. And this is the way you have to look at it. If you look at it on the left, right, that's your setup. This is now tilted in 2 directions, right? The base station, of course, doesn't tilt. It's on the ground. So it stays the same. It doesn't have any problem with the GNSS receivers tilting because, in theory, it's measuring to the electronic center of the receiver, right? Which there will be a small allowance which you can build in the software, the difference between the center of that and the center of the prism underneath it when it's tilting, right? But that's not a big deal to work out. So what you do is you're actually measuring in real time, or near real time, all the angles, all the distances, right? And the GNS receivers are giving you an X, Y, Z position. Now, we're taking Z into account here as well. Now, if you go back to your close range photogrammetry, a topic you'll never forget, if you remember, when you had a bunch, or laser scanning, a bunch of points here, right? And they're like moved around. You've got a bunch of points here that are less moved around, so they're known, control, or thousands of points, right? You normally do between the two what's termed a helmet transformation. It's like a fancy affine transformation, more than 6 parameters, right? You can go through the mathematics here and work it out. So that's what's going to happen. Is when you get tilting it, you're going to do normally what will be a helmet transformation. Another clever way of looking at it, someone taking basically the helmet transformation is a very old photogrammetric term, right? If you imagine it like this computer screen is what you're measuring, right? Because it's tilted all over the place, right? On here, there's a few things you know, which are these 4 corners, or 3 of the corners, right? And this is actually the design. You can do the transformation between here and here in real time. Therefore, you know what the X, Y, Z changes are, right? Helmet transformation usually is at least 6 parameters. So X, Y, Z, tilt, you know, so you have skewness and things like that. Basically numbers, that's all it is. So you can plug in another number here that's on the design that says the center of the column, right? At 2 meters above the floor. And then that transformation will tell you where that is at that instance. So that's how this point here, which we've used simply as a single point, actually can be set out at that point to where it's supposed to be by design. You know, so the person setting up the formwork will be going, this doesn't look good, but you know, I'll trust you. So when it straightens up, it should be at that point. Now we're talking about some fairly sophisticated software. You are talking about trying to get to real time because it's going to change every second, right? There's not a lot of papers on this because no one, even the building people, don't want to give away how they went about the construction. But it does seem as though the particular formwork on that used a sliding scale. So they got to a point where they were actually able, they didn't sort of lock it down until a series of measurements were made. And then once it was at that point, that was it. So they did test it extensively, but it hasn't been adopted in every single super high rise because I think it's been used twice, 2 other cases I know of. Because you can see it's a fairly expensive exercise to have all this equipment set up on every floor with a lot of measurement. Right? But look on the other side, in this particular building, there were no options. Okay, so the transition between systems, this is the one that's different for you as surveyors, is that when you get to a certain point, right, and I say here, about 100 to 250 meters, you must transition from what you're doing at the bottom because there is no other option. Right? So as surveyors, if you're looking at this task, it's no longer a repetitive task. If I was doing a construction survey for a highway, M1 upgrade, right, probably the equipment There'd be a difference between the equipment I'd use for the control, most likely GNSS, right? Installing the control on the highway, right? There might be slight differences if we've got a big bridge. We might use more precise equipment and different control. But basically, everything else is going to be a repeat of the equipment, personnel, skill set, and approach, right, as you go along. You know, with the high rise, it's different. As you go up, which is in theory the progress, right, you're going to have to change the way you think, right, your methodology, and your equipment, which is a bit unusual because for surveyors, you can see why for super high rise it probably is the realm of people with who specialise in this area. You know, what you've got to gain out of it is actually understanding it, because if you look at it here, there are things you learn, like you saw in metrology. You're most likely never going to buy a laser tracker, right? It's not the sort of thing you buy. I mean, you can buy a PlayStation 4 for what, $400, and you can buy a laser tracker for 130,000. Which is the more useful? Seriously, you know, it's like look at it. But understanding these things allows you to move into other areas, right? You've just got something put into your head here, going, so I can actually integrate GNSS. What would happen if I actually had a tilted, something I can't even set the instrument up on? Can I actually bolt the instrument to the floor at an angle like this and measure? And you think, well, if I did a transformation between that and the flat, I could transfer those points to what they would be if we're on a flat plane. Yeah, it's waking your thinking up a bit. All right, so there's a whole lot of stuff in the book that explains, parts of it. This is the ECB tower, so this is the one in Germany I talked about, right? Yeah, quite large. You know, it's not exactly small. The one on the left is actually a very interesting thing. This is Vladivostok, right? Okay, which is in eastern Russia. You know where Vladivostok is? Eastern Russia. Okay, it used to be famous because you couldn't go there, because it was the major Russian naval base of the West. The only thing that went there was the Trans-Siberian train. But nobody wanted to go as tourists, so the Trans-Siberian now goes to either Moscow, right, or further south, you know, or stops in Mongolia, right? Because tourists actually want to go to Beijing, but they don't want to go to Vladivostok because it's like 30 below most of the time and there's nothing there. But this big bridge, you can see the tower is splayed out, right? And the height of this tower, the pylon height, is 226 metres. That's actually pretty high, right? So they had the same problem with that, is that they had to, how to plumb. And it's not vertical, but we're using the term plumbing. So they had inclinometers placed all over it, but they also did a similar system to what we just talked about, the Burj Khalifa. They did it in real time. So when the inclinometers were giving information, right, they were able to link it to the survey set out to go, at this point in time, that should be there, right? So like someone putting a skyhook up, you know, going, I'll hold it there, and then we'll build around it. And then with the next bit, we'll redo it all, right? So it had a lot of inclinometers, a lot of issues on how to resolve it. Once again, like, you may get involved in that, even though I can't see a Russian firm hiring you to go to Vladivostok, right? Actually, I can't see a Russian firm hiring you, but because your Russian's fairly poor, I gather. Yeah, just average. Yeah. But you apply that and just say, in a simple view, you've got a structure that's tallish and it's not really vertical, right? How are you going to go about it? That's what should be coming out of this course, is you go, I want to think in 3D space, right? What could I do? You know, what's feasible? How can I adapt the equipment I've got? Now, maybe there isn't some simple solution, but that's what is the new way of this. I mean, young surveyors now are having to think, how do I use a UAV to make money? How can I efficiently collect data, right? You know, that type of thing. Okay, so this is almost like a summary of the course as well, to a lot part of it, is that understand the object of the survey, right? And the other people involved. Almost like the assignment question. Now, that's a statement. It's not that simple. Anyone who's worked on construction is that the senior civil engineer thinks differently to the site engineer, right? Thinks very differently to the structural engineer. Certainly thinks totally different to the plumber, you know, and the foreman. Well, foremen are particular people, breed to themselves. So they think differently to everybody else, right? You know what I mean? And so you actually, to understand the way they're thinking is difficult. So you've got to give yourself that survey issue, right? And you've probably seen that I pushed in the modules. It's not about problem solving. It's about stating the problem. If you state the problem, you've usually got the tools to solve it. Okay, give yourself options, right, for a measurement plan. You know, sometimes you will have to tie yourself to actually, we've got this equipment, right? You know, so I'm limited to that. You may not buy another total station, but what did Stephen say the other day? He saw a GAC2 precise level for sale for $5,000, right? You know, which seemed a bit expensive to me. I'm sure you can get a cheaper one than that. Right? So I think you can look for other options. You're not going to go and buy a total station 1 millimetre and 1 part per million, you know, for one job, right? But you may look and say, can we hire one for parts of the job? This is really hard. Understand in detail the specifications of the task and to translate into geodetic, surveying terms. Because most of the things we've been discussing is it's non-surveyors talking to you, right? And they don't talk in the same terminology. Surveyors don't talk to each other often in the same terminology, so you hardly expect other professions to do it. So you're the one who's got to interpret. Now, usually the way is you don't go, oh, I'll interpret later on. You be the proactive person. So when someone says it's got a tolerance of this, right, in writing you find out what the specification for that is. So they're saying the beam placement structure over the holding down bolts, right, it's got a tolerance of 10 millimetres, right? You're going to say, is that in all directions? Is it 95%, 99%, right? It doesn't matter if they don't understand. It's irrelevant, as long as they sign off on it. Because then you've got something to work to, right? That's a very important aspect. That it's hard to interpret in the communication side, but it is actually important that you fully communicate what both parties are thinking. Otherwise, even the compliance survey gets to, I think in one of the, was it module 2? You know, where one of the specifications was over a 3 metre rule, you know, the surface of the road shall not deviate by so much. It actually doesn't say along the road or across the side, or, you know, so that's the sort of thing where it reads okay in a specification, but you must clarify yourself. Now, understand the cost. That's what the engineer will expect you to do, right? Even though most of this, it's your cost that you're worried about. And the one that isn't there is actually resource constraints, including resource constraints knowledge. Because once you leap out of this standard thing, someone who's been building roads for a zillion years, right, and surveying them, doesn't need a lot of new knowledge to keep on doing that. If you're going to move outside of the normal surveying, right, and a little bit outside it, go over the fence a little bit, then you need the knowledge or be able to get it. And understand on how you decide on a model. This is one of the things to develop a model, but how do you pick which one you're going to use, right? Best way is to simulate. Try to think ahead and simulate its actual application. So if you're doing a high-rise, for example, if you really want to get into this business, you go and have a look at the way people are doing it now, seeing what the pros and cons are. And give yourself fallback options. Now, I don't mean fall off the building, right? But if something doesn't work, what could I do reasonably quickly to actually fix it up? That usually means, have I got redundancy? Don't always think of redundancy as being like an extra control point. Redundancy might be equipment, another method of actually calculating it. You know, that is also redundancy. Okay, and here's a quote, because I always put quotes on here, right? But this chap who's doing it's Cranenbrook. He's the guy that the principal developer of the Burj Khalifa thing, right? Became pretty famous for it, you know. And I think he's exactly right, because this isn't the surveyor of my era, all those years ago. This is the surveyor of your era, right? Yeah. You have to survive, you have to change. Now, okay, to survive as a surveyor years ago, you had to change, but the time period you had to change over in was probably longer. Right? You know, you had more time to change. You got less time to change now. You have to be inventive and creative, and you have to reverse a lot of things that you've learned. You can presume the stuff you've just learned here, that you don't have to reverse it tomorrow, right? At least get past the assignment and the exam before you reverse it. next one, thinking outside the box. People, talk about this, right? But you can actually study it. You can go and read De Bono and a whole bunch of people that write stuff on lateral thinking. Won't do you any harm to read, right? And you will see there is an approach to lateral thinking. The next one is something that is just a common problem in the profession, whether you be from a technician level, students, or graduate surveyors, or even experienced surveyors. There is still too much of, I press the button, I get an answer, it must be good. Right? I don't need to know what's behind it. Professionals, even surveyors, actually think that it's relatively easy, right? We don't actually explain the complexity to others very well. You should look for challenging projects. We have had a pretty dead period in surveying, like mapping the entire country was challenging. Surveyors did it because they wanted to be part of this big thing. Building the bridges Asia and Europe, which goes across which strait? There's only one place where Asia and Europe goes across water. Bosphorus in Turkey, right? There's a bridge there. One of the first very, very long span bridges, right? Engineering and surveying feat. People who worked on that would have been very proud of it, right? So you have to start thinking differently, right? And the last expression, exactly right, is if you're in the 20th century, if you're not an artist, this is an artist with equipment, mathematics, thinking, right? Then you are not going to survive. And you don't think that you will survive because I think there's one or two surveyors general left in Australia. It was less than 100 years ago where the second top person in government in all states was the Surveyor General. Right? The most powerful position outside of the Premier. Things change dramatically, right? Now, fortunately our profession is changing and you have some pretty dramatic people out there. And it depends. Huh? Yeah, but you're the latest mobs. I mean, you can choose to how you do it, right? But this last module is, if you look at those 4 photographs, you realise that if you don't like heights, it's probably not a good one to really worry about. Just get through this one on the assignment and the exam and think, I'm going to stay on low rise and, roadworks, right? The one on the bottom right, it scares me to look at it. It's so, it doesn't look very encouraging, does it? Okay, thank you. There's a bunch of stuff that's worthwhile recommended reading in the study book, right? And on the study desk. And in the study book, there's more of a case study of the Burj Khalifa, right? It's worthwhile going through.